Analysis and design procedure for reinforced concrete tall buildings. When we start doing the design of the building, we have to start the conceptual design. After we get the architectural design from the architect, we have to develop the structural system. That one is the preliminary design stage. In schematic design stage, we have to select the structural system for gravity load resisting system as well as the lateral load resisting system. In selection of the systems, we have to consider the load paths, materials, and approximate size of the structural members. And if we need to do the seismic design, we have to consider the primary mechanisms for the inelastic response of the building. If the building is not in seismic zone, you need to consider only the elastic design for the lateral load for wind. So, in consideration of the load path, we have to consider how the gravity load will transfer to the foundation, as well as how the lateral load will transfer to the foundation. For example, for gravity load, if we use the flat slab system or beam and slab system, the gravity load will transfer from the slab to beam, and beam to column, and then column to foundation. For lateral load system, we have to consider the load path. Normally, for seismic load, the load is generated from the mass of the structure. So, the seismic load will generate from the mass of the slab, and then it will transfer to the moment frame or shear walls, and then it will go to the foundation. Then we have to consider the material properties, the strength of the materials. Are we going to use high strength concrete, 8000 psi, or low strength concrete? It depends on the size of the building. Normally, for tall buildings, we use high strength concrete for the vertical members, like shear walls, columns. So if we use high strength concrete, the member sizes will be smaller. And we have to, but horizontal members, we use the lower ones. Horizontal members will maybe 5000, 6000 psi, but for the vertical members, for tall buildings, we use about 8000, 9000, sometimes 10,000 psi. Then we have to estimate the size of the structural members, like the shear wall thickness, size of the column, depth of the beam. After we determine the size of the preliminary size of the members, we have to discuss with architect. We need that size for the thickness, so the architect needs to adjust. If there is conflict with the architectural design, he has to revise. And then we have to, for seismic design, we have to think about the primary mechanisms of the inelastic behavior. Where we want to, in seismic design, for the normal buildings, we do not design the building to remain elastic under strong earthquakes. We allow some damage in the building when the building responds in strong earthquake. So we have to decide the locations we want to allow the damage, the yielding of the members. If we design the core wall building, we have to think where the core wall we allow to yield. We want to allow to yield the core wall in flexure at the base of the wall, or at the mid height of the wall, or if we design the core wall, shear wall with the moment resisting frame, we have to also think, we want to allow the columns to yield or not, or we allow the yielding in the only in the end of the beams. So those kinds of things we have to decide. We estimate, okay, this location might yield, for example, in beams, we assume that, okay, the beam will yield at the end in flexure. So we have to put proper confinement in that zone, and due to that yielding of the beam, what will be the maximum shear? And we have to consider we have to calculate the probable shear demand due to the moment capacity and design the beam that should not fail in shear, but we allow the yielding in flexure. So the beam moment demand will exceed the moment capacity, but shear demand should not exceed the shear capacity. Those kind of things we have to consider in the elastic mechanisms. And after that, we have to start the model with our approximate sizing and check the dynamic response as well as the lateral load response of the building. In terms of dynamic response, we conduct the modal analysis and check the mode shapes, natural periods, modal participating mass ratios of the building. If the mode shapes and natural periods are not acceptable, we have to revise our structural system. For example, we use the structural system, dual system like core wall, as well as the moment resisting frame. The building is 40-story building, and we start analyze with the cross section properties, and we found that our natural period is 7 seconds. It should not be. For 40-story building, it should be around 4 seconds. So it means that our lateral stiffness is not enough. So we have to increase the lateral stiffness of the building by adding more shear walls, or increasing the length of the wall, or maybe increasing the size of the moment frame. Those things we have to adjust at the preliminary design stage. And then and also we have to check the mode shapes of the building. Normally in seismic design, we prefer the first two modes are in translation, and the third mode will be in torsion. So if the first vibration modes are in torsion, the building is likely to vibrate in torsion behavior under seismic. So we do not want that kind of behavior. So we have to tune the dynamic response of the building by, for example, if the left side of the building is very stiff, we add the shear wall in the left side, and at the right side we do not have. So the building will be in torsion mode. So we have to, if we cannot add the shear wall due to architectural constraint, we should stiffen the moment frame in that side. So those kind of things we have to tune at the schematic design stage. That is important. If we do not do the schematic design properly, and we continue the detailed design, we will have a lot of problem in the detailed design stage. When you calculate the reinforcement at the detailed design stage, the forces cannot be manageable. Sometimes when we check the required reinforcement, the reinforcement are too high because we do not develop the proper structural system. And secondly, we have to check the lateral load response parameter for the base shear of the seismic loading, wind loading, as well as the base moment, lateral displacement. If the lateral displacement are beyond the within the acceptable limit or not, and the wind, under earthquake. But in earthquake, in code-based design, there is no limit. But for wind, people use about H over 400, 300. It depends on the engineer's judgment. and story drift. But story drift, we have limit in both seismic and earthquake. Normally, story drift for tall buildings, for design level earthquake, we check the limit at 2% drift. Story drift means the relative displacement between two floors. The upper story displacement minus lower story displacement divided by the height of the story. If the story drift is very high, if the relative displacement is very high due to lateral loading, the partition wall may be damaged due to large displacement. And also we have to, if we use the dual system with the shear wall and moment resisting frame, we have to check the shear distribution between the moment frame and the shear walls. So those kind of check we will, how to check in depth we will explain in the next lectures. Okay, these are the structural systems that I explained before. For gravity load system, we use beams, slabs, girders, columns for the primary to support the gravity loads. And lateral load system, we use columns, shear walls. If we use the steel brace, there will be bracings for lateral loads. And another system is the floor diaphragm. That one is for to transfer the seismic loads. Normally, seismic loads develop in the floor due to the mass of the floor and the acceleration of the floor. So that's inertial forces has to transfer to the lateral load system by the floor diaphragm. Actually, the floor diaphragm is a slab, a gravity slab only. So normally, when you design the slabs, we design only for the vertical load, out of plane bending moment and out of plane shear. We never design we hardly people normally do not design the in-plane forces to transfer the diaphragm, the inertial forces. Those things also we have to check in the seismic design. This is the schematic of the structural system. Here, this is the shear wall. This is the shear wall to resist the lateral load. This one is the gravity load, and due to the seismic load, lateral load will generate, and this floor diaphragm has to transfer these inertial forces to the shear wall, as well as if you have the moment frame, it has to transfer to the moment resisting frame. And also this at the ground level, this is the basement. So this now the shear, the seismic force from the diaphragm transferred to the wall at the top floor and then lower floors, it will accumulate in the shear wall, and then that force has to transfer to the foundation system. So lateral load has to will transfer from this wall to the foundation, and also transfer to the basement walls and transfer to the surrounding soil. So in this level, the shear force in the shear wall will transfer to the retaining wall by the ground floor diaphragm. So the shear will transfer from here to here. There will be large shear force in the floor, and also there will be some tension and compression force in the shear wall, and it will transfer to this retaining walls. And not all the forces will transfer at this level. Other basement level also transfer, and it will and remaining force will transfer to the foundation. So when we design the building, we have to check we have to do the design for the entire load path. If you have the inclined column, you have to check the axial force in the horizontal members connected to that inclined column. The purpose of the lateral load resisting system is to transfer the lateral load applied at any location in the structure down to the foundation level. Normally, primary lateral loads that we design are wind and seismic loads. In seismic design, when we select the structural systems, we have to check the seismic level of the seismic intensity of the project site, and if we construct in the low seismic zone, the expected ground motion will not produce the large inelastic displacement in the building. So we can use moderate ductility structural system like intermediate moment frame in the moderate and low seismic zone. But for high seismic zone, we should use the high ductility lateral load resisting system like the special moment resisting frame and special reinforced concrete shear walls. If we construct the building in the low seismic zone, the seismic force will be small and the wind and gravity design might prevent. And the structure might have more reserve strength to resist the seismic load. And also the code permits to use the structural system and configuration with low energy dissipation capacity. It means that less ductility, low ductility structural system in the low seismic zone like concrete intermediate moment resisting frame, ordinary moment resisting frame, and concrete braced frame. But for high seismic zone, we have to use the high energy dissipation capacity structural systems. High energy dissipation means if the structure is yielding, the energy is dissipated. For seismic loading criteria, you have to select the first. You have to select the code. Which code are you going to use? UBC 97 or ASCE 7, or maybe the local building codes like Thailand building code or other Indian building code. So those things you have to determine first and then prepare the design criteria. This is the sample design criteria from ASCE 7. I will explain you briefly about that parameters that we consider in seismic loading. In ASCE 7, first ASCE 7 is generated for United States. They conduct the seismic hazard assessment and prepare the seismic hazard map for the code. First, you have to select the seismic design parameter for 2,500 year return period earthquake, which is called maximum considered earthquake. That one is in ASCE 7 we have to check for two natural period. One is for short period 0.2 second, and another one is for long period 1 second. So that natural period is the building natural period. So you can estimate that 0.2 second is the building height will be about 2-story building. 1 second means 10-story building. Normally we estimate the natural period based on the number of story of the building. For 40-story building, it will be approximately 4 seconds. So you can see that we estimate only for 10-story building. So if we design with this code for 40-story building, these parameters are reliable? So the code generate only 2 seconds, and then for the other natural periods, higher natural periods, 3 seconds, 4 seconds, 5 seconds, it has the it has an equation to estimate those parameters. So normally the codes are developed for the low-rise buildings and mid-rise, approximately 10 to 15-story building. But for the tall buildings, that's why people start using new technologies and approaches like performance-based design. And for the seismic input, they conduct the seismic hazard assessment for that site and for that building natural period, not directly using from the code. The code has only 2 natural period, and other natural period it estimate by the formula. But now some people conduct the site-specific seismic hazard assessment for particular building and get the seismic input parameters. So okay, I'll continue that one. So we extract 2,500 year return period for 2 natural period, and then we have to convert it to the soil type of the site. These the first 2 parameters are based on for the site class B, for the hard soil. If the soil is not good, if the soil is soft at the site, we have to amplify the demand forces. The forces will be increased. So we have to now, okay, in this example, the site class is E. Normally, the code gives these 2 parameters are for site class B, the first. So for site class E, we have to magnify the forces by the factors. These factors you can find from the code. So I have to multiply 0.77 with 1.176. So we will get the another parameter, adjusted parameter according to the soil type. So our domain is increased, these 2 parameters. But these are for 2,500 year return period. But in the code, we do not design the building to resist the earthquake of 2,500 year return period directly. We design the design basis level earthquake, not MCA, not maximum considered earthquake. The design basis level earthquake, which has the return period approximately 475 year. So that level earthquake we design, and that level of earthquake is approximately 2/3 of that MCE domain. So we multiply with 2/3 to get these parameters. Then we design it. Then the code says that if we design the building for this level of earthquake, the building will perform well for that level, and there will be some damage, but there is no no risk for the life safety of the occupants. But in reality, earthquake can come very high magnitude as well as the very small magnitude. So the code says that if we design for this level earthquake, it is because this earthquake can come 500 year interval. So this is already strong earthquake. But if the minor earthquake come, small earthquake come, the building will not damage, and it can be it will behave as it will behave elastically, and also we can reuse the building just after the earthquake. No need to repair the building. And in case if the maximum earthquake which can occur at the site in 2500 years, the strongest earthquake come in that building, the building will not collapse, but there might be a lot of damage and the building might not be reused. The code assumes like that, but we design only for this level of earthquake. If you design this level, the 2500, if the strongest earthquake come MCE level, the building will not collapse. We assume like that. If the small earthquake come, the building will not have damage, and it can reuse immediately after the earthquake. And another important thing is this response modification coefficient. It depends on the structural system of the structural system that you selected. If you select dual system which has shear wall and intermediate moment resisting frame, in the code it gives this R value of 6.5. If you use high ductility, high energy dissipation capacity system, this R value becomes higher. Actually, when we calculate the seismic force, we calculate the elastic force and then divide by this factor. So the factor is the actual design force is reduced. And this is the sample response spectrum curve for DBE level earthquake. So in the code, it gives at 1 second this spectral acceleration and 0.2 seconds this one. That portion it is estimated by the equation. And this is the natural period of the building. This is the building response. And this one, spectral acceleration, that one is not the acceleration of the ground. That one is the acceleration of the building. Depends on the natural period. For example, if you have 20-story building, okay, 2 seconds, the acceleration of the building will be 0.3 g. This is just approximation. And then when we calculate the seismic design force, this 0.3 g is the acceleration. And you multiply with the mass of the building, you will get the design base shear. Do not confuse with the ground acceleration. But if your building is completely rigid, it is not possible. So the building will shake same acceleration as the ground. So if the building is completely rigid, the natural period of the building will be 0. And it will this value will be same as the ground acceleration. You can determine the peak ground acceleration of the building. Peak ground acceleration of the earthquake will be the starting point of the response spectrum. So after you make the model and check the after you make the model, you have to do the analysis and check the analysis results. In structural analysis, in these days, there are 3 phases. One is modeling, and then the second one is computation, and the last one is results interpretation. Once you construct the model, you have to model to capture the important aspect and behavior of the structure. But you cannot model the structure exactly same as the real structure. You cannot do that one, but your model should have the sufficient accuracy, economy and detail for the practical purpose. You do not make too much details, but you have to model the building to get some reliable results. That one is important for the designer. For computation, we do not need to worry too much. Normally, computation process is done by the program and computers. It is a complex process and involving the finite element theory, complex logic, and extremely large numerical computations. If you are a programmer for developing the structural analysis software, okay, you need to know those things in details. But it is better to know the theoretical background of those computations. But in real projects, you do not need to do by yourself. These things will be done by a computer. And the last one, interpretation. That one is is very important. After you do the analysis in computer, you will get the results, but you have to interpret to make the design decisions. And also, not only understanding, if you can feel the you have to develop the feeling for that structural behavior. If you see the value, okay, let's say bending moment diagram. In the bending moment diagram, you will have 500 kilonewton meter, for example. You can feel that value is big or not, or it is manageable or not. That kind of feeling you have to develop, the feeling and skills to interpret the results. For example, if you design the core wall building for 40-50 story building, and you get the bending moment at the base of the wall, let's say 10 million kilonewton meter. You have to think, when you see that value, you should know that value is reasonable or manageable. You should know those kind of things. Then normally the core wall building we design for 1 to 5 million kilonewton meter. So those kinds of things can be developed by experience. It is normally they were not taught in universities. So when you do the real projects in future, you have to when you get the normally people do the analysis, just model, analyze, and then click the design pattern. So, and it will produce you the program will produce the reinforcement directly. They did not see the bending moment diagrams, shear force diagram to understand the structural behavior. When we study for undergraduate, we have to draw the shear force diagram of the beam, bending moment diagram of the beam, by hand calculations, many different approaches in exam. But okay, now when we work, we do not need to draw these diagrams. We can get these diagrams easily from the program, but we do not see it and check it. We just directly go to the reinforcement calculation. So those, when you do the checking of the forces and diagrams, and you understand the behavior, if the forces are not correct, you have to recheck your model, revise your structural system, and do the analysis again. Otherwise, if you do the reinforcement calculation, it is waste of time. And then you cannot manage the forces, and then you have to go back. So before you do the detailed design, you have to interpret the results to get the proper understanding. this is the modeling stage. In modeling stage, we have to model the materials and member sections, as well as the boundary conditions. If you considering the soil structure interaction, if you do the design for seismic loading, you have to consider the damping. For materials in the code-based design, we normally use the nominal strength of materials. That nominal strength doesn't mean the actual strength; it is the lower strength. Actual strength, when you design for the, if you use the concrete strength of 4,000 psi in your design, but in the building that concrete strength will be more than that. And when you consider, and then you have to model the section properties of the materials, of the member sizes. Normally we use the cross section in the wind and gravity load analysis, and for the seismic analysis we use the crack section. We reduce the moment of inertia or shear stiffness of the members to consider the redistribution of the forces during the earthquake. But that estimation is not accurate, because, for example, in the code suggests to reduce the stiffness, of the beam 0.35 G in ACI. So that one is, we will reduce all the beams in the model. In earthquake, all beams will not damage. Some beams will damage, some beams will not damage. So those kind of details cannot be captured in the normal analysis and code-based design. And soil structure interaction. We have to normally people use hinge support, fixed support directly in the model, but we should consider the proper soil structure interaction. Consider the when you make the fixed support of the column, but in reality it will not be fully fixed. There might be small rotation, but you assume that it is fixed. So if you model the soil springs properly at the foundation, you can capture accurately for the behavior of the structure. If you have the basement walls, you have to model the horizontal soil springs to consider the restraining effect of the soil. These spring properties can be calculated based on the substrate modulus of the soil from the geotechnical investigation reports. And for the damping, normally we use 5% damping for the reinforced concrete structures. Just put the damping percentage in the model. This is just approximate value. That damping includes the response from the energy dissipation, the damage of the members, yielding of the reinforcement. So we assume that this is 5% damping. For beams and slabs, we normally use the frame elements, and we have to model the proper insertion point and length and offsets and end releases. These things I will explain you in ETABS when I present how to model in ETABS. Okay, how to define the insertion point, how to define the end length offset. Insertion points means you have the beam rectangular beam, but in model you want to connect with another beam at this point or this point or this point or at the center. So these kind of things. And for the end length offset means when the beam and the column connect there will be overlapping area at the joint. So that region are we going to consider when we calculate the length of the beam. Those things we have to if we consider that normally program use the centerline modeling, so the connection point will be at the middle of the joint. If we do not want to use that location, we can give the command to program to shift that joint to the edge of the column. And releases are the sometimes we want to connect the beam with the column with the moment release pin connection. If you want to use that one, we have to release the moment in the model. Normally we model the slabs with shell elements, and we prefer the semi-rigid diaphragm to calculate the actual lateral stiffness of the floor. Actually, semi-rigid diaphragm response and without diaphragm response, they are same.
That's clear.
Yes. And for the shear walls, we use the shell elements. And coupling beams, we can use either frame or shell elements. Normally we use frame elements, but if the coupling beam is very deep, we should use the shell elements. Those beams we have to provide proper confinement, because those beams will yield extensively under side spring, because this is connecting the wall and there it will have large bending moment, so it can yield at the end or maybe at the to do the shear force. It depends on the size of the configuration of the beam. And for the foundation modeling, if your foundation is the pile foundation, we normally model the piles as the frame element, and we model entire length of the pile, and we apply the lateral sway spring in the pile to model the interaction effect of the sway. If we model the pile, we can check the forces in the pile and also do the design of the piles directly from the program. Some people do not model the pile. They model the spring, one spring to represent the pile. If you model like this, you can get the response of the building same as the model with the piles, but you cannot check the forces and design of the piles. If you have only the mat foundation, you have to model with the shell elements, and you can use either area or point springs. These are the analysis procedures that we normally conduct for the code-based design of the building. After we model, we always check the modal analysis before we check other things. From modal analysis, you can check not only the lateral stiffness or natural periods motion of the building, you can also check if the model is correct or not. For example, when you draw the elements and they are not connected properly, when you do the modal analysis and when you see the mode shape, that member will vibrate only. The entire building is still, but only that portion is vibrating. So you have to correct the model. Okay. And another case is dead load. Dead load is people normally use linear static analysis, but we prefer to use construction sequence analysis. In ETABS, that feature is available that you can add the structure story by story, and analysis is continuing according to the construction. So it can capture more realistic response of the building. Because after the construction, at the after the construction of the one floor, at the construction site, the engineers will level the columns and the shear wall at the same level after one story, and it will continue to another story. So the program analyzes according to that sequence. But if you use normal linear analysis, the program will analyze entire building at one time, and then it will give you large differential shortening between the members. Like if you have the shear wall and the frame pyramid around the shear wall, so shear wall stiffness, axial stiffness is very large. It will not shorten a lot, but column stiffness is, axial stiffness is small, it will shorten more. So after the linear analysis, you will see very large differential shortening between the wall and the column. But in reality, it will not be that much. It will have, but not too much, because you analyze at only one time. So due to that response, the beam connecting the wall and the column will have large shear due to that differential shortening. So to avoid those things, we should contact the construction sequence analysis. And for seismic load, we use equivalent static analysis or response spectrum analysis. But these days, we always use response spectrum analysis. Static analysis is suitable for simple building. And for wind load, we use the linear static analysis. So, in difference between static analysis and response spectrum analysis, in static analysis, it cannot consider the dynamic response of the building properly. But for response spectrum, it considers the dynamic response. Okay, this is the modal analysis. Modal analysis, we consider check the vibration modes, and we can check adequacy of lateral stiffness and torsional response, and then we can tune the structure to be dynamically regular, and also we can determine the principal directions of the building. I will explain you how the principal directions of the building can be determined. Normally for rectangular building, if you have the rectangular building like this shape, principal direction will be this and this direction. But for L-shaped building, it will not be X and Y. You have to calculate according to the stiffness. That one, it can determine from the modal analysis. For example, for rectangular building, if you apply the seismic force in this and this direction, you will get the maximum design forces. Okay. In reality, we do not know which direction, where the seismic force earthquake will come. And the earthquake will excite in this direction as well as this direction. But we cannot design the building to apply the earthquake 360 degree. Many cases, we just design two direction only, X and Y. So, in case if the earthquake comes diagonal direction, the X and the design from X and Y direction, the member capacity that is designed from X and Y direction is adequate or not. We are not sure. So, if you now in theory, if you design the building, if you apply the seismic force parallel to the principal direction of the building and design the building, that one will be the conservative one. That one will give you the maximum design force in the building. Okay. So, for example, L-shaped building, we have to find the principal direction first, and then apply the earthquake force in that two principal direction, and then check the design. So this will give you the largest force that can occur in the members. Another thing is the mass source to conduct the modal analysis and seismic analysis. We normally consider the 100% of the dead load and 25% of the live load. When we do the gravity load design, we apply the live load for residential floor like 1.92 kilopascal. But that in reality, that live load will not exist. Only 25% might exist. So we do not consider 100%
For the model analysis.
for modal analysis and seismic analysis. Seismic loads also calculated from the mass that you define. Okay, this is the sample analysis results of the from the modal analysis. This is about 45-story building. Okay, this is the first mode. This building is rectangular shape. So the first mode here you can see this is a core wall, and there are some shear walls here, and also there is the moment resisting frame. This is a typical floor plan. So the building is weak in this direction. So the first mode is in this direction. Here this one is the first mode, 5.192 second, and we are showing from this direction. And second mode of the building is this one, T2, 5.13 second. This is in X direction vibration. First one is Y direction vibration. And third one is this one is torsion. Here I showed you in black. This one you can see in black it is Y, this is X, and this is torsion. This is the typical response of the building. This is torsion is 3.5 second. We prefer that torsion mode should be far from the first two mode. Let's here this is 5.1, 5.19, 5.13, and this is 3.5. So it is less likely to happen. This natural period is different. Sometimes difficult to make it far. For the small buildings, the 100% of the mass of the building is participating in these first two modes. This is for the small building. But for tall buildings, in the first two modes, 40 or 50% of the mass is participating. So other mass, remaining mass, is contributing in other modes, like this kind of shape, this kind of curvature, it also participating. So we have to consider these effects due to higher modes. For example, if 100% of the mass is participating in these first two modes, the bending moment diagram in the building is swaying like this. So bending moment diagram will be like a cantilever beam. The bending moment will be largest at the base of the wall. But higher modes are also dominated. So now the wall can bend like this. The wall can bend like this. So bending moment will maybe high in the mid height of the building. So that's why shear wall can yield at the mid height as well. This is about construction sequence analysis. Like I already explained, the building is not constructed at one time, and it is so differential shortening can cause the moment and shear forces in the horizontal members. This is how to create the construction sequence analysis. this one I will show you in depth. This is response spectrum analysis. This for seismic analysis, the behavior of the building is due to the vibration. This is the internally generated forces due to the building mass, and also this ground shaking, and these forces depend on the shaking of the ground and the stiffness of the building.
Mass of the structure.
Yes, the stiffness has. Yes, it also. Yes, it also depends on the mass of the structure, because that natural period depends on the mass and the stiffness. Okay. So we cannot say that if the building is very stiff, the forces will be high, or if the building is very flexible, the forces will be high. We cannot conclude like that. It depends on the response spectrum. Here, I will go back. Here, you have to see. For example, if you design for 2-story building, okay, the forces will be here, approximately. But if you design for 10-story building, the forces will be high. So you can, the spectral acceleration will be high. That's why if you multiply with spectral acceleration and mass of the building, it will generate the forces. So normally when we measure the base shear, we also mention with the percentage of weight of the building. The base shear is 5% of the total weight of the building, 10% of total weight of the building, like that. So you can say that if your building is completely remain elastic for 10-story building, the spectral acceleration is 0.6 g. So it will be 60% of weight of the building, the base shear is. This is if the building remains elastic, that we reduce by R factor. Okay. So we can, but if building is very tall, okay, the force will, percentage of force will be reduced because it is very flexible. But in this zone, we cannot say if it is stiff, the force will high or low. We cannot say. So it means that the design force depends on the ground shaking as well as the lateral stiffness of the structure. So, in general, we can say that okay, if the building is flexible, the force will reduce. So we can not say that if we want to reduce the force, we will make very small lateral stiffness. We cannot do like that. If you make very small lateral stiffness, during the earthquake, the building will sway too much, so it can create problem for the occupants. So we have to adjust the stiffness as well as design the required strength. But when you design the wind, it is reverse. If your building is too much flexible, the wind force will increase. So we have to. There is a factor in wind loading, so we have to take care of that one. When you design the tall buildings. Normally, we do not run the time history analysis in code-based design. And most of the engineers use the response spectrum analysis in basic design. But for static methods, we use only for the very simple and regular structures. Mostly we use the response spectrum analysis. The difference between static analysis and response spectrum analysis is the distribution of the forces. That when you do the static design and the dynamic static analysis and dynamic analysis, the design base here is same, but distribution of the forces in the model, they are different. In response spectrum analysis, it considers the dynamic characteristic and it will distribute according to that characteristic. And if your building has a torsional mode is dominant, so it will consider those effects more accurately. And also for the tall buildings, you must use the response spectrum analysis at least because of the higher motion effects. Static analysis cannot capture those effects. Static analysis is just apply the inverted triangle loading on the building and analyze it. So it is not accurate. Okay, principal directions. In the codes, it doesn't mention about the definition of the principal direction of the building. But we can determine the principal direction based on the component of the base reaction from the mode shapes and calculate the resultant force and get the angle between resultant force. Here is the sample. First run the model analysis and then you get the base shear of mode 1 vibration mode. So from analysis, mode 1 base shear, for example, in X component and Y component, X component is 1041 kilonewton negative direction and Fy is 846 kilonewton in positive direction, and then we calculate the angle between X and Y components, and then we will get the principal direction. So in this building, the principal directions are shown in dotted line. So we should apply the seismic force in that direction to get the maximum design force. When we do the seismic design, we have to consider the directional and orthogonal effects. Seismic forces can act two directions simultaneously, but it will not act. It will not shake the building with the maximum acceleration at the same time. So when we do the design, we normally consider 130%, 100% and 30%. 100, it means that one direction we apply 100%. In another direction we apply 30% only. That one we can define in the load combinations. But I think in bridge design, some people use 140. The one that I showed you, the response spectrum that I showed you is the elastic response spectrum. When you run the response spectrum analysis, without scaling the results, it will give you the elastic base shear. As I mentioned you, when we design the building, we never design to respond the building as elastic. We allow damage, so due to that damage, the energy will be dissipated and the shear, design shear will be reduced. We have to reduce the base shear. Normally, when we reduce the base shear, we use the base shear resulting from the static lecture of equivalent static procedure, which is in the code there are 3 or 4 equations, and then we calculate that base shear from those equations, and then scale the response spectrum analysis results equal to that base shear. It depends on the code. If you use UBC, you have to scale the base shear 100% equal to the equivalent static base shear. This is how R value works. When you run when you run response spectrum without scaling, your structure will behave elastically here. Okay, this is the elastic displacement of the structure, and this is the base shear of elastic base shear of the building. Okay. But if we allow the damage, the structure will yield at certain force damage, and then it will not reach to the elastic domain. So how? So in the encode, this one is drawn by pushover analysis. We encode, we scale the elastic forces divided by R. Okay, and then we will get the design base shear here. We design for this one. But when you analyze the building, you are analyzing linear analysis. From the analysis, you will get the when you check the base shear. Okay, base shear is okay, design base shear. But when you calculate the displacement of the building, you will get this displacement. But in reality, this is not the actual displacement. Building is yielding and displacement will be high. The force is not increasing, but the displacement is increasing. So in code, in ASCE, we have, after you get this displacement, you have to multiply with another coefficient which is called CT. And then you will, to estimate the inelastic displacement of the building. This is the inelastic displacement. But in UBC, there is no factor for CT. You have to multiply that with R to estimate the inelastic displacement. Those factors are developed based on the assumption that elastic displacement and the inelastic displacement are same. In seismic design, important coefficients are this R factor you need to understand, and CD. Okay. CD is to check the displacement, R is to determine the design force, and another factor is the omega naught. That one is also to determine the design force. So normal structures, okay, we design our design force is divided by R. This one we design it. But if you have the transfer system like this one, okay, the lower structure which is supporting this column should not yield. If it is yield, the structure will be unstable and fall down. So, this lower structure has to resist the force, maximum force occurred during the earthquake. So, for that lower portion, we have to design this level of force. This is the maximum force that can occur in the system. So, we have to multiply back with omega naught for those members in the design. So, the lower part of the structure can resist the maximum force during the earthquake. This omega naught is approximately 2.8. You can find in the code in UBC and both ASCE. I will explain you later where this one is used. Okay? You can for the transfer system as well as the diaphragm design. After you do the modeling and analysis, and then you have to continue the structural detail design of structural modules. You have to design for beams, columns, shear walls. If you have the coupling beams, you have connecting the walls. You have to design the coupling beams and slab, diaphragm, foundations. If you have pile foundation, you have to design the piles as well. So, for structural design of beams, there will be two types of beams normally. One is a beam which is carrying only the gravity loads, and another one is which is carrying both gravity and resist the lateral load. For gravity load beams, we call it secondary beams, and we can design only for gravity load combinations. But for the beams in the moment resisting frame, those beams we have to design for lateral load as well. For the beams, we check for flexure and shear capacity. And for the columns, we check for PMM interaction and shear. If you design the column for gravity load alone, the shear will not be dominant. But if you design for lateral load, you have to consider the shear carefully. Another one is the shear walls. For the shear walls, you have to consider both PMM and shear. But in shear wall, you have to check only for in-plane shear only. But in column, you have to design for two directions, one V2 and V3. And another one is the doubling beam. Doubling beam, you will have to do conventional reinforcement and diagonal reinforced coupling beam depending on the configuration of the beam. For conventional reinforced beam, you have to design for flexure and shear like normal movement resisting frame beams. But for diagonal reinforced beam, you have to design for shear using the diagonal reinforced. And for the slabs, you have to design only for the gravity loads, for the out of plane response, for shear and flexure. But for diaphragm design, you have to consider in-plane forces for flexure, shear and axial forces. And for the foundation, for structural design, you have to check for flexure and shear out of plane, and also you need to check for the bearing capacity, which is based on the geotechnical report. Piles also, for structural design, you have to design as column, PMM and shear, and also you have to check the geotechnical capacity of the piles, nozzle bearing capacity. These are the design configurations of the structural members. This is the capacity design approach for the beam. This one I already explained in last semester. When you do the beam design for moment resisting frame, you have to consider the probable shear and following the capacity design approach. And also you have to take care for the strong column beam check for the special moment resisting frames. These are the typical reinforcement details. This is the reinforced concrete shear wall details. In shear walls, you have to provide the proper confinement if your compressive stress is beyond the limit. This is for diagonal reinforced coupling beams. This one you need to design only for shear, no need to design for bending moment. The main reinforcement is this one. This is just minimum requirement. The stirrup and the longitudinal reinforcement, they are just for confinement only. So this is for diaphragm design. For the diaphragm design, we have to check for the axial forces, shear forces, and the flexure design. Here, this is the ground level diaphragm, and the shear force coming from the shear wall will be transferred through this diaphragm to the retaining walls. So we have to transfer through there will be three load paths. One is this shear will transfer through this portion by shear to the retaining wall, and this side it will transfer through the axial. If this one is moving this direction, this one will be axial compression, and this end will be axial tension. So we have to provide the horizontal reinforcement in this direction to transfer the axial forces, as well as the shear reinforcement in this part, as well as in this other part. And if this one is close to retaining wall, in this side, shear will be higher in this side. So this is the reinforcement for the tension and compression. If we check the diaphragm at the tower level, we call the inertial force from the slab will be transferred to the lateral load resisting system shear wall through this reinforcement. So these reinforcement, we call it collector bars, because these bars collect the inertial force from the slab and transfer to the wall. This is at the tower level, and then wall will carry the lateral forces and start transferring at the ground level. So the shear force accumulated in the wall will transfer to these bars. These bars will distribute the force to the retaining wall. So we call it distributor. If it is distributed the shear force from the wall to the foundation element, so we call it distributor. Another thing is, this is the typical floor plan of the tower, and if you have the two walls here, if the earthquake load is coming in this direction, the inertial force will act this direction, and these two walls will act as a support. So you can consider this slab as a beam. So because of this inertial force, there will be bending in this slab. At this portion, this will be tension reinforcement, and this will be compression reinforcement. So we call these reinforcement as squat reinforcement to resist the impede bending moment in the diaphragm. So in diaphragm design, we have to check compression forces in the collectors and compression and tension forces in the collectors and distributors, as well as the force reinforcement, and also the shear in the diaphragm. This one also will have shear because you have the bending moment, and it will generate the shear force in the diaphragm in this direction. So that reinforcement should be in addition to the reinforcement that you provide for the gravity loading. For example, you provide the reinforcement 12 mm dia bars at 150 mm spacing, and then you calculate the reinforcement for the diaphragm. You need another 12 mm dia at 100 mm. So 100 millimeters finish. So you have to add that reinforcement in addition to the gravity load reinforcement. This is the collector reinforcement which is coming from the shear wall. Another important item that you have to consider is the backstay effect. This one is especially for the tall buildings. In tall buildings, you will have the large podium and also the large basement. So, when the lateral load comes, this podium diaphragm, if the podium diaphragms are stiff, it will generate the couple to resist the overturning moment due to the lateral load. So due to that backstay effect, the forces in the shear walls may be reduced, but we have to but the diaphragm forces at the podium level and the ground level might be increased. To consider the backstay effect, this is from performance-based design. Here ETC 721 suggests to use the upper bound and lower bound backstay effect. It is to consider the stiffness of the diaphragm with the upper bound and the lower bound. For example, we use the larger stiffness in the diaphragm and check the forces in the diaphragm. If you use the larger stiffness, the force in the impelling forces in the diaphragm will be increased, and you design the diaphragm forces. But foundation forces will be reduced. So to get the conservative results for foundation, we use the lower bound backstay effect. For example, if you use 0.5 Ig for upper bound, for lower bound we use 0.2 Ig for the diaphragm. Okay, mat foundation. For mat foundation, we have to check for flexure and shear. Normally we check the shear capacity of the mat first to determine the thickness. After we design for shear, we continue the flexure design. Normally we do not provide the shear reinforcement in the mat foundation. We try to design the shear demand to resisted by the concrete alone. But sometimes we need to, if there is a limitation for the thickness of the mat, we need to add the shear reinforcement. In mat foundation, we have to check for one-way shear as well as if you have the columns, you have to check the matching shear as well. And when you check the shear for the one-way, you have to check distance D from the support. No need to check at the corner of the edge of the wall. Okay, this is the overall design procedure for the tall buildings.